Great, so this brings us to our first keynote. We're going to have two keynotes during the workshop. First keynote is by Rachel Lin, who's a professor at UC Santa Barbara, and she has amazing results on obfuscation from constant-degree encodings, and she's going to tell us how they work. Thanks.
Great, thank you, Dan. Thank you very much for having me here. It's great. All right, so as said, I'm going to talk about I/O or indistinguishability obfuscation from DDH-like assumption on constant-degree graded encodings. Okay, I know there's lots of jargon here. Don't worry, I will explain slowly one by one. All right, so the focus here, also the focus of this workshop is about circuit obfuscation, or even more general program obfuscation. What do we mean by that? We would like to have a way to compile a circuit as you would imagine they look like, and or gates with wires, and they might have some secret embedded inside it. And we want to compile such a circuit into another one that preserves the same functionality in the sense that on every input it produces the same output, but now it becomes unintelligible in the sense that any malicious attacker looking at the compiled circuit would have a hard time to reverse engineer to figure out whatever original secret embedded in the starting point circuit. Okay? And of course, for such a compiler, we will call such a compiler an obfuscator. Okay? So obfuscator is the compiling mechanism. And we would like definitely that this compilation only incurs some small slowdown, in particular polynomial slowdown in the size of the circuit. Okay? So in terms of this unintelligible, what does it mean? Well, it's very intuitive, but it definitely backs definition, right? And in the literature, there has been multiple definitions of formalizing different levels of security that capture this meaning of unintelligible. And what we're going to talk about today is really the weakest notion called indistinguishability obfuscation, or I/O. What I/O hides is really only one bit of the information. That is, which one of two equivalent circuits, C1 and C2, is being obfuscated here. Okay? So here by equivalent, I mean those two circuits have the same size, as well as identical truth table. And if these two conditions are true, then we would like the compiled circuit or the obfuscated circuits to be computationally indistinguishable. They are computationally hard to tell apart. Okay, so great. Ever since I/O was proposed, there was basically a long time period there was silence about how to construct it. Until 2013, this is how we feel like. There is a box parachuted down into our community, and everybody curiously gather and open the box, and we find the first I/O candidate construction. Okay. And since then, there has been an explosion of work on what I/O can do and how we construct I/O. So 3 years after today, in 2016, first of all, we have way more different constructions of I/O. And furthermore, through the boat of I/O, we have successfully traveled through what we call the crypto proper land, which we used to operate in, to this crypto wonderland. And in this crypto wonderland, a lot of new things, tasks that we used to want to do but don't know how to do, like full general purpose functional encryption, or tasks that we didn't even think about doing before, like gobbling Turing machines or run computations in time independent of the time complexity, now all become possible. And really, the list of new feasibilities enabled by I/O is way more than what I could put on this slide. And furthermore, I/O also, not surprisingly, go back to imply a lot of the classical primitives in crypto proper land, like FHE. So it seems like I/O, this primitive, is really charting for us a broader map of cryptography. And this is great. Okay? Unfortunately, the picture is not really as victorious. Why? Because it turns out all those I/O constructions are only candidates in the sense that we do not have high confidence in their security. Furthermore, they're all built on this complicated algebraic structure, which we call graded encoding, and I will tell you in a moment. And in the past 3 years, there has been an extensive effort trying to instantiate this algebraic structure using integer lattices, and multiple proposals were made. Unfortunately, all of them were shown vulnerable to a line of very powerful zeroizing attacks. And in fact, there are new attacks that directly attack the I/O candidates when they are combined with those concrete instantiation of graded encoding. I know I'm missing some new references here, but it's just hard to keep up with the speed how things are developing. Okay. So I think it is not an exaggeration to say that we're really balancing at the border of security and insecurity. And this is not a state where cryptographers would like to be in. We would like to be as far away from this insecurity border as possible. Okay. So this somewhat unsatisfactory state of art really reflects an underlying lack of understanding. In fact, we have very limited answers to some of the most basic questions you would ask about any cryptographic goal. For example, what cryptographic object imply I/O? What assumptions imply I/O? In the tradition of cryptography, usually these two questions are the first to be answered when we look at any cryptographic goal. It turns out in this case, not in the context of I/O, it's not the case. In terms of object, through one route or the other, all those I/O constructions end up relying on polynomial degree graded encodings. In short, there's this complex algebraic structure that supports homomorphic evaluation of polynomial degree polynomials. Okay? What about the assumptions? Most of the I/O candidates are analyzed, assuming the graded encodings are ideal in the sense they're implemented using an all-powerful, a stateful oracle. Or assuming there's some very strong assumption called the Uber assumption that captures closely power in the ideal model. There are only two exceptions. Based I/O security on relatively simpler assumptions called, for example, the multilinear subgroup elimination assumption. Okay? So all in all, that there's currently a huge gap from what we know can imply I/O to the more standard tools that we use in cryptography. For example, degree 2 graded encodings. There are bilinear maps, which do exist and has been used extensively. So motivated by this gap, the question that we focus on asking is that, can we build I/O from simple objects and assumption? Okay. And it turns out there has already been some progress. This year in Eurocrypt, I presented an I/O construction from constant-degree graded encodings. What are they? They're basically a much weaker version of what we saw before, in the sense they only support homomorphic evaluation of constant degree polynomials. Okay? A drawback of this work is, however, that we rely on the strong Uber assumption on those graded encodings. And as you recall, that Uber assumptions are very close to ideal implementation, and we would like to be more concrete. And this is the focus of this new work, collaborating with Vinod Bankantanathan at MIT. What we show is that when we use constant degree graded encodings, Uber assumption is not necessary. In fact, we can base the security on a much simpler DDH-like assumption called a joint SXDH. And this shrink the gap from what is standard. In particular, degree 2 graded encodings, bilinear map, with exactly SXDH assumption. Okay? All right, so now let me start to become more concrete about defining properly all these terms that are appearing on this slide. Okay? To start with, I need to tell you what are really those graded encodings. It seems like a very powerful abstraction, algebraic structure. And I will start with introducing multilinear maps defined by Dan and Silverberg in 2003. And they're really the most natural generalization of bilinear maps. In particular, you have a collection of groups, and you can encode a ring element in the exponent. Okay? And in order to be consistent with notation, I will use this bracket notation, where the index of the group is written at the lower right corner. Okay? And what can you do with such encodings? First, you can homomorphically add. if you get encoding with the same label, okay? in the sense that they're encoded in the same group. Also, you can zero test in the sense that give me any encoding, I could tell whether the encoded value is 0 or not. Okay? Why? Because you always have the generator of the group in hand, and you can just, or if you have the identity of the group in hand, then you can compare. And the magic of multilinear map is really in this homomorphic multiplication capability, that you can take a bunch of encodings with different labels. So this would correspond to the asymmetric version, and homomorphically multiply them to get an encoding of the product in a target with a target label. Okay? And the degree of this multilinear map is exactly how many encodings you can multiply together. Make sense? All right. Now, graded encoding goes further, one step further to generalize multilinear map. First, we no longer necessarily associate encoding with a group. You can just think about some kind of encoding mechanism that can encode a ring element with a label. Okay? In particular, the encoding mechanism could be noisy, could be randomized. So there exist multiple encodings for the same element and the same label. Homomorphic addition happens just as before, but now because the encodings are possibly noisy, zero testing is not for free, and in fact can only be done at a special label called the zero testing label. And finally, a powerful change is that multiplication can now be graded, in the sense that you can incrementally multiply two encodings with different labels together and get an encoding of the product at the price that the labels add up. Okay? The reason that this is graded is because that the output encoding now can be further computed upon. It can be further paired with some other encodings which we couldn't do in the case of multilinear map. I see some frowning, so if there's any question, just ask at any time. Yeah.
For the addition and subtraction, can you do that indefinitely?
You can do that indefinitely as long as they're in the same with the same label.
So that they don't add up even if they're noisy? The noise somehow like...
The noise does add up a little bit, but I assume by saying that infinitely, we still mean polynomial number of times. Question? Okay. All right. Great. So there's this notion called a parable, in the sense not all labels could be paired together. There's this additional constraint that only those labels that satisfy the relation called a parable can be paired together. Okay? And this gives you the graded encodings. So all in all, with these three different operations, what you can do essentially is that you can homomorphically evaluate a polynomial, get an encoding of the output, and test whether the output is actually 0 or not. As long as your polynomial satisfies all the label constraints, in the sense that addition happens between the same label, multiplication happens between parable labels. Okay? And the degree of a graded encoding is simply the maximum degree of all the polynomials that could be homomorphically evaluated and zero tested. We will also care about two additional parameters. One is called the universe size, which is the number of labels. You could think about this as how many correlations I have to create. The more the labels are, the more kind of sets of encodings, the correlations I have to create. And we'll also differentiate between prime order and composite order, in the sense that whether the ring that the graded encoding operates on is prime order or composite order. And when we talk about ideal graded encodings, what do we mean? We simply mean that there is an oracle in the sky that implements this interface of the graded encoding for us, and that is the only thing that you can do. Okay? So it is a very, in some sense, much more restricted model. Great. So in summarizing, the difference between polynomial degree and constant-degree graded encoding is really in terms of a functionality. When we talk about constant degree, we provide a much weaker functionality that I can only evaluate constant degree polynomials as opposed to high arbitrary polynomial degree polynomials. And in fact, the two of them also has some qualitative difference. We all know that when the polynomial degree just is implemented in the ideal way through an oracle, it actually implies the strongest notion of obfuscation, called the virtual black box obfuscation, which turns out to be impossible to instantiate without any oracles, okay, or in a plain model. On the other hand, we do know that ideal constant degree is not capable enough to instantiate VBB obfuscation. Okay? So that is one way that they're separated away. And furthermore, the same line of work also showed that constant degree JES actually does not help constructing I/O in a black box way, in the sense that if you manage to obtain such a construction, you can just remove this constant degree JES from the construction. Okay? So this is about the functionality. What about assumptions? As mentioned so far, that most of the I/O constructions are analyzed in the ideal model. And the first attempt to try to base I/O on concrete computational assumption is done by Paz, Seth, and Tilan. That they proposed the Uber assumption that closely capture what can be done in the ideal model. And then there came this simplification in the assumption proposed by Gentry, Leho, Saha, and Waters, this assumption of a multilinear subgroup elimination. And all these assumptions are postulated over polynomial degree graded encodings. And the two new works depend on only constant degree graded encodings. And furthermore, the second work, which we're talking about now, has a concrete assumption, simple assumption. In terms of some other parameters, the second work also only rely on prime order graded encodings as opposed to composite order, and has a constant universe size in the sense that there are only constant number of labels that we need to operate on. Okay? So in short, the new work is the only work that has all three nice features. Okay. So I hope I have built up enough kind of suspense for you to want to know what is this assumption. Okay, so let's get into it. Before I can tell you what is joint SXDH, as the name suggests, I will first tell you what is SXDH, right? So SXDH is basically the classical decisional Diffie-Hellman assumption on one label. What is it? Well, if I give you encoding of a DDH table AB, where AB are sampled at random, under some label L, a single one, then this distribution should be postulated to be indistinguishable from encodings of all random elements with the encoded under the same label. In addition, keep in mind that the attackers always know all the encodings of ones in every group. Okay? Encodings of ones correspond in some sense to generators of groups, and they're just public. First thing to notice is that this assumption is not true if we could actually pair label L with itself. How? You can simply take encoding of A and encoding of B, pair them together to get an encoding of AB under the label 2L, and then take the encoding of AB and the encoding of 1 under L, and pair them together to get another encoding of AB. And you can compare whether they're the same. And this way, you can easily distinguish those two distributions. Therefore, the constraint is that encoding with label L do not multiply with itself. Okay? If this constraint holds, then this assumption possibly holds. Okay? All right. So now I am going to tell you what is joint SXDH. It's basically extending the DDH to many labels. Instead of looking at just one label, we'll look at multiple labels. What we want is that if I give you the joint distribution of the same DDH tuple AB, encoded and now under a set of different labels belonging to this set S, and I would like to have this joint distribution to be indistinguishable to encodings of A, B, and R, the same set of random elements, also encoded under the same labels. Okay? And clearly, some constraints are in need. In particular, the constraint should be that any two labels in the set, Li, Lj, should not pair together. Suppose they can, then I can launch again the same attack I just mentioned before with respect to the SXDH to differentiate encodings of AB and encodings of R. Okay. So, any question about this assumption? Okay, great. All right. So that's it. This is the assumption that we use. And as mentioned, that our assumption will work over graded encodings with constant degree and the constant number of labels. So everything is constant. So now I'm ready to state the main theorem is that we give a non-black box construction of I/O from constant degree graded encoding, assuming sub-exponential joint SXDH assumption, as well as the existence of a sub-exponentially secure PRG in NC0. And because all the components that we use, the assumption we use are sub-exponentially hard, the resulting I/O is also sub-exponentially hard. Okay?
So I think at this point everybody asks, what's the constant?
Yes, I'll talk about it.
Oh.
Yes. Okay, so our assumption on the PRG is a strong one. We need the PRG to have polynomial stretch and sits within the simple class of NC0. Exists some candidate construction. In particular, GORA has random NC0 functions, which basically corresponding to a random system of KCSP with respect to a fixed predicate Q. And currently, there are no successful attacks if Q is chosen in a careful way. Okay? And in the rest of the talk, because everything is sub-exponential, I'm just going to assume sub-exponential implicitly, so that allows me to just talk about the object. Okay? All right, so exactly as Dan is asking, everybody asks, what is the degree? All right, so this is roughly the degree. The degree is roughly 6 times the degree of the PRG in a ring R. Okay? I am going to explain. What is this ring, first of all? This ring is exactly the ring underlying the graded encoding we use. Okay? In the sense that we're going to, in the construction, evaluate the PRG inside the graded encoding. Therefore, we care about the degree of computing it in this ring. And more formally, what is the degree? The degree is the degree of the arithmetic circuit that can compute the PRG over the Boolean cube in R. Okay? To note that, first of all, that this degree is actually bounded by locality of this PRG. What do I mean by locality? Our PRG is in NC0. Every output bit depends only on a constant number of input bits. This number is called the locality of the PRG. Okay. Why the degree is bounded by the locality? It's because that PRG has binary input string. Therefore, any polynomial that computed is multilinear. Okay. So now, what can we plug into it? In the literature, there exists a locality 5 PRG candidate for which the best attack is sub-exponential time. Okay? So just kind of allows us to assume that it is sub-exponential time. And if you plug that in, the degree will be roughly 30. It will be a little bit higher than that, but the ballpark is 30. Yeah?
If there's an arithmetic circuit that's a PRG instead of a Boolean one,
I do need a Boolean one.
you need a Boolean one?
Exactly. Yes, it's a very good question. Okay. All right. Great. So next, I'm going to talk about our approach. Okay. So how can we construct I/O from constant degree JAS with just joint SXDH assumption? Our approach is 2 steps, just like most of the I/O construction. The first step is try to reduce the task of constructing I/O to the task of constructing something simpler. In particular, in this work, we're going to try to construct functional encryption for NC0 functions. Okay? And we will require the functional encryption to have very good efficiency, which I call linear efficiency. And this is so for the purpose of this talk, I'm basically going to gloss over the efficiency issue. Okay? the step where we'll use this additional assumption of the PRG in NC0. Okay. And then in the second step, we'll use the graded encoding to construct such a functional encryption. The first step compared with what previously we can do is that it's incomparable, but previously we can only bootstrap I/O from FE for NC1, however, do not need this additional assumption of PRG in NC0. The proof turns out to be extremely simple and is inspired by previous works on multiple ones. And so the main technical contribution or the technical challenge really lies in the second step of trying to build such FE for NC0 from constant-degree graded encodings. And in the rest of the talk, I will focus on the second step. Okay. So what are those functional encryptions? So I will stick with the secret key version because for the purpose of bootstrapping to I/O, public key or secret key does not matter. Okay. So let me stick with the secret key version. Functional encryption basically is this beautiful extension of it's like a normal encryption, but it allows you to do partial decryption. What is it? Well, like a normal encryption, you can generate a secret key. You can encrypt input using the secret key to generate a ciphertext. Now, the new part is that you can also generate a special partial decryption key associated with some function f. We call the secret key for f. And if you decrypt a secret key using such decrypt a ciphertext using such a secret key, what it produces is exactly the output of the function evaluated on the encrypted input. This functionality allows us to do the following. One can publish a set of ciphertexts for different input xi's and publish a set of secret key for different function fj's. And by the functionality, we can already evaluate all possible output fj on xi. Okay, there's a quadratic, in the sense, a quadratic number of outputs. What about security? The default security cares about hiding the inputs in the sense that it should guarantee that one can only learn from this set of ciphertext and secret key or the possible outputs as guaranteed by functionality and all those functions. And any additional information about the inputs remain hidden. One can also think about a stronger security called function hiding, which naturally cares about hiding both the input as well as the functions. So the only thing that is revealed are those outputs. Okay. All right. So in order to construct FE for NC0, we're talking about this very simple class, which is just NC0 from constant degree jazz. Our basic idea is that we would like to leverage some of the work that has already done in the literature of functional encryption. In particular, those FE schemes that can be built without graded encodings. It turns out that without graded encoding or I/O, this huge hammer, there's very limited things we can do. Basically, we can do FE for computing inner products. But we can achieve the stronger security called function hiding, right? And we'll call such FE schemes inner product encryption or IPE. We can indeed build these things from the SXDH assumption on bilinear maps, which are basically degree 2 graded encodings. Great. So the main idea is to try to bootstrap I/O for inner product to not I/O, to bootstrap FE for inner product to FE for NC0 using this constant degree graded encoding, as well as another tool called the randomized encodings. Okay? So let me tell you about those two tools. One is the IPE, the other is the randomized encoding. So what IPE can let you do, as we said, that they allow you to compute inner product. So you can release a secret key associated with a vector and release a ciphertext associated with another vector. And when you decrypt this pair of secret key and ciphertext, it reveals exactly the inner product of those two vectors. And what function hiding guarantees you in this setting is that if you get a bunch of secret key and the vector and the ciphertext for one set of vectors, and you get a bunch of secret key and ciphertext for a different set of vectors, they should appear indistinguishable. as long as it holds that all the possible quadratic number of inner products are identical. Okay. So in this work, we actually only need a weaker version of such IPE in the sense that we just need the IPE to reveal whether the inner product is 0 or not. We do not need it to actually reveal the entire inner product. And such IPEs can be constructed from degree 2 graded encoding. And how do these constructions actually look like? Not too surprisingly, they basically look like the secret key and the ciphertext are graded encodings of some randomized version of the original vectors. Okay? How you randomize it depends on the master secret key and some random coins. And you encode those randomized version using the degree 2 JES. And through pairing, one can naturally compute an encoding of the inner product because inner product is exactly degree 2. And once you get an encoding of the output, you can test whether the output is 0 or not. Okay? Another tool that we use in this work are randomized encodings. This is a very beautiful notion in cryptography, which basically allows you to represent a complex computation using a much simpler randomized computation. So that the simpler computation produces an encoding that basically allows you to recover the original output and reveals nothing more. So there are different measures. When we say simpler, what does simpler really mean? There are different measures of simplicity, and in this work, we particularly want the notion of simplicity that the simpler function is linear in the input x. Therefore, you could actually represent every encoding element produced by the randomized encoding as an inner product between the input and some coefficient vector that will depend on the function and the random coins. Okay. As you can see that there is definitely a connection between the inner product encryption that we use and this type of affine randomized encoding. Additionally, all the computations that we consider here are over some ring, in particular the ring underlying graded encodings, as opposed to be binary. Such randomized encodings exist, and it was constructed by Appelbaum, Eshai, and Kush-Levitz, and their encoding also has multiple special properties that become very handy in our construction. Okay, great. So now with these tools, we are ready to play. Okay? In the next 4 slides, I'm going to tell you the main ideas of the construction of FE for NC0. And if you follow those 4 slides, you've got most of it. Great. So the goal is to do FE for NC0. We have a function in NC0, a very simple one, f. And we would like to come up with those secret key and ciphertext that will decrypt to f of x, okay, in a secure way. So the naive idea is that, well, we have this very fancy tool called graded encoding, right? Can do homomorphic evaluation and can zero test the output. Let's put it in use. Why not just encode the input using graded encoding and use the graded encoding homomorphic evaluation to compute the function? What do I mean? Well, I can just publish encoding of the input as the ciphertext. Evaluation or decryption means take the function as is, evaluate it using graded encoding to produce an encoding of the output, and test whether the output is 0. Great. This really means that functionality is not a concern. Why? Because the graded encoding is a tool powerful enough to support NC0 computation. The issue is really lies in security. Why? Because we really want to rely on simple assumptions on graded encodings. And if you recall, the assumption that we use only hide information when the encoded values are almost random, right? Their ABRs completely random. Unfortunately, if I use it to encode the input is definitely not random. Can just completely reveal the input, in fact. Nor any of the intermediate computation result is random. Therefore, security does not hold.
What's the role of the secret key in this?
there's no secret key. It's a naive idea. There's no secret key. The secret key is F itself. Yes, it's indeed very naive. All right. Yeah? I see, because what I get is an encoding of the output as opposed to the output itself. Okay? So in particular, I can test whether the output is 0 or not, guaranteed by the graded encoding functionality. And this will be good enough for bootstrapping to I/O. Okay? All right. Great. So how can we achieve security? We want to hide the computation, right? This is why we need function hiding IPE. Recall that it will allow us to hide some computation in the product computation. It's a very modest capability, but it is something, right? And the goal is that the question is, how can I bootstrap from hiding in the product to hiding NC0 computation? So we're really doing bootstrapping in a very nano scope. And this is why we need this randomized encoding. Recall that randomized, why? Because randomized encoding really allows us to represent a complex computation using a simpler one. In particular, why not just use this inner product encryption to compute affine randomized encoding? Remember that our randomized encoding can be represented as an inner product between the input and some coefficient vector, right? And in order to simplify the talk, let me play the ostrich and make a simplification that assuming our randomized encoding has only one element inside. So I don't have to worry about computing each one of those elements. And this element is an inner product. Well, everything fits. What else to do? Well, use this IPE, the secret key encode the coefficient vector, and the ciphertext encode the input. Great! If I publish this, when I decrypt, I will be able to get an encoding of the inner product, which is exactly an encoding of the randomized encoding. Makes sense. Seems like we have made progress. Now the next question is, well, I don't really want the randomized encoding. It represents the output, but it's not the output. It's the output that I actually want, right? So next question is, how do I decode this guy so that I can get the actual output? Well, I haven't really used the graded encoding yet, right? You can do complicated homomorphic evaluation, which I have not put to use. So let's do that. Instead of instantiate this IPE using a bilinear map, as they were constructed with, let's instantiate it with a constant-degree graded encoding, which is a generalization of bilinear map. Why do I do that? It's because I want the encoding of the randomized encoding to be in a label that could be further computed upon. In particular, I can just take it and homomorphically evaluate the decoding algorithm to decode this randomized encoding under the hood until I get an encoding of the output. Yes? Yes, yes. This is a special property of the AIK randomized encoding, that the degree of the decoding is exactly the degree of the computation itself. Good question. Once I have an encoding of the output, again, I can zero test and good enough. What about security? Well, also follows pretty easily is that I used an inner product encryption, which is a function hiding to compute the randomized encoding. Therefore, it should hide everything else except from revealing the randomized encoding itself. And then, by the security of the randomized encoding, it further hides the input. Okay. That's it. Okay. Looks like most of you got it.
Why is it necessary to homomorphically evaluate the decoding function on the encodings? Why can't you recover the randomized encoding and then do the decoding here?
Because we used an arithmetic randomized encoding, so the encoding itself is not binary. Yes.
What's the problem that it's not binary? You do it in the, this is like part of the encryption, right? You don't have any computational restrictions.
I don't have any.
Or you do want the whole thing to stay?
Just a second, because this is sort of like the, how should I say it? So we want to, so the question is that whether I could use a binary randomized encoding, right? Suppose there is a binary randomized encoding, I just compute this binary randomized encoding, and then just extract it and then evaluate it. Right?
Okay.
So we're not using a binary randomized encoding, we're using arithmetic randomized encoding. Therefore, the randomized encoding itself is actually
You say that the elements of pi are not bits, they're ring elements?
right, they're ring elements.
I see. So you can zero test and get them out, right?
Yes, exactly. And I'll tell you why. It exactly transfers into my next part, which is great. Why? Is because this randomized encoding needs randomness to compute, which I have glossed over so far. In order to compute those random bits, it actually is very tricky. In the end, the only random bits that we could manage to get are ring elements, as opposed to binary random bits. Therefore, we have to use randomized encoding that takes ring randomness as its randomness. And therefore, what they produce will also be ring elements. Okay. Does that answer your question?
You are using Boolean PRG somewhere, right? That's how you get the degree to be 6 times.
Yes, the Boolean PRG, however, is in the bootstrapping step. And right now, we're in the step of constructing the FE for NC0. Okay. Great. So, yeah. Well, I haven't told you about it yet. Yes. Thank you for noticing all the loopholes, because that's it. Turns out is not quite. There are actually many challenges. That was just kind of the basic framework of how this whole construction works, which I think is simple enough that everybody could get. And now, let's go on playing. That it turns out there are many challenges in making this framework work. One is that particularly difficult one is how do I generate the randomness for different randomized encodings, which I didn't talk about. How do I generate, remember that we made this kind of simplifying assumption that my randomized encoding actually has only a single element. I actually, in reality, need to evaluate multiple elements. And in fact, the non-functional function hiding IPEs do not really produce an encoding of the inner product as we described, which was very handy for us because I can just get the randomized encoding and continue to compute. It actually computes the inner product masked by some random scalar, which if you think about, really prevents further computation on top of it. And also, we can actually implement a public key functional encryption for NC0 as opposed to secret key. But so far, all the components I use are function hiding IP. They're secret key primitives, and they definitely do not give you public key primitive. All right, so I don't have time to go over all of them, and I will just tell you the most difficult one, okay? How to generate randomness. All right. It turns out that this simplistic security intuition, which is a right intuition, does not really work. Why? Because if we want to reduce to the security of the randomized encoding, we must guarantee that all the randomized encoding are generated using independent and truly random strings. However, if we look at it in this construction here, the randomness are hard-coded inside the secret key, right? Because the randomness are the ones that are used for producing those coefficients. And the problem is that if I take the same secret key and use it to decrypt multiple different ciphertext, they will all produce randomized encoding using the same randomness. And at this point, randomized encoding guarantees nothing. To see this more clearly, that imagine a scenario where I publish m different secret keys for different functions. and I publish m different ciphertexts for different inputs. The functionality guarantees that I can take any pair and try to decrypt that pair, and it will produce the inner product inside the encoding. In particular, I will call that inner product the randomized encoding for function fj evaluated on function fi evaluated on input xj, and I call it pi ij. So I need m square pieces of randomness to generate all those m square randomized encodings, but I only have space m. Why? There are m ciphertexts and m secret key. So how do I generate those randomness? Well, the classical approach, as one would first think of, is, well, let's use a PRG. It turns out that PRG doesn't work here. Why? We're doing this nanoscope operation inside of inner product. Right? The computation is so simple that it does not support a PRG evaluation. Turns out for PRG, either the degree will be too high, or you will have to use a super long seed, which would not fit inside the space m. So the idea is that, well, let's maybe there's something already there in graded encoding. In particular, there may be some built-in pseudo-randomness in graded encoding, in particular, joint SXDH, right? So DDH already, this is a classical trick used again and again in cryptography, is that if I give you encoding of a bunch of SIs and then a bunch of TJs, the matrix of their product is indistinguishable from the matrix of random elements. This simply follows from classical DDH. So this is great. This looks like a very good PRG for us. First of all, the seeds are very short, which are those SI-TJs, has exactly size m. Second, the computation is very simple. It's only a quadratic computation, could fit into inner product, right? And this is precisely why that I will only get random elements over the ring as opposed to random elements in binary. So to see how this idea could be put into work, let me make another oversimplification, is that I just directly assume this randomized encoding is computed by inner product, the input, and the randomness itself. I know it doesn't make sense, but trust me that this already will allow us to see how we solve this problem. So now the idea is that I can multiplicate share this randomness R as the coordinate-wise product of random vector S and T. Okay? And now I can compute this inner product by computing S inner product with T multiply X. So I basically separate those two multiplicate share at two different locations. And then we're going to encode those SIs inside the secret key and all those TJs inside the ciphertext together with the input. If I now take a pair of them and try to decrypt, it will give me exactly the right inner product, which is the randomized encoding. And even better is that now every randomized encoding, the m square ones, all have distinct randomness. None of them share randomness. Why? Because the ijth one will have randomness Rij, which equals to Si multiply Tj. Okay? But just saying that all these things are distinct does not necessarily mean that RE security would apply. I really need these things to be pseudo-random. But this is good enough, right? As we just saw in the last slide, that the product would be pseudo-random under the hood inside the encodings. It turns out that this hope does not really work. I know there are lots of terms. All right, why does it not work? Remember that those secret key and the ciphertext, what are they? As we said, they're encodings under some labels. In particular, they're encoding of randomized version of the vectors we want to encode, which means they will encode Si in some label L0 and Tj under some label L1, and they are pairable. Because that's all how we compute the inner product, using pairing to compute the inner product. If you think about it, what the attacker will see is that they will see Si under L0, Tj under L1, and SITJ under label L, which is the product label. They absolutely is easily distinguishable from random. Okay? So this kind of points to a conundrum. It seems like it can never get to work. Why? Because I want these things to multiply, but if I want them to multiply, I can't hope that they are pseudo-random, right? I can't have like two things that are together. They're just like head-to-head. And this leads to our next idea is, well, I'm going to use the function hiding property of the IP to move those TJs inside the security proof. Why? How? Instead of just directly encoding SI and TJs, I'm going to encode them with some trailing useless zeros. Okay? They're useless for the honest execution, but they will be extremely useful in the security proof. Why? In the security proof, if I want to argue about XI is hidden, what I will do is that I will use the function hiding to move to a hybrid, where all the randomized encoding for XJ are actually directly hard-coded inside the secret key. If you look at the before and after, they produce identical outputs. And therefore, by the function hiding property that these two are indistinguishable, these two versions of secret key and ciphertext are indistinguishable. Now, great. If you look again, all those SIs, TJs, SITJ product are all in the same label. And therefore, we can apply SXDH to argue that they are pseudo-random. Okay? Great. So I made these two simplifying assumptions. One is that this inner product is, this randomized encoding has only a single element. The other is that it's just as simple as computing the inner product between the randomness and the input. None of them is true. So in reality, we have to overcome them. And in reality, the coefficient vector could be arbitrary polynomial in the randomness. What we could handle is that as long as these polynomials are the sum of a polynomial number of multilinear monomials over R, then we can deal with it. It turns out that this property is satisfied by the AIK11 randomized encoding construction. The first the first issue is actually more problematic, especially combined with the fact that all those IPs do not compute encoding of the inner product, but compute the inner product masked by a randomness. So for that is the real reason that we need the joint version of SXDH as opposed to just SXDH itself. The final construction looks like this. We're going to have multiple pairs of secret key and ciphertext from the IPE with very carefully planned seeds and labels. And when you evaluate all those pairs, you get exactly encoding of the randomized encoding masked by some random scalars. And you can evaluate the decoding algorithm to get the encoding of the output. Security works because joint SXDH help us to guarantee that randomized encoding security holds, and from which we can argue the FE security. That's the whole picture. Great. All right, so let me summarize. In this work, we built I/O from constant-degree graded encoding from a DDH-like assumption. Okay? And this brings us much closer now than before to what is standard, basically bilinear map with exactly SSDH. The obvious question is, what's next, right? Can we bridge this gap? Okay? There's some very exciting new works trying to build I/O from concrete low-degree multilinear maps. Okay? One work is by Amit Shahai and Prabhanjan Anath and Amit Shahai that, at least I know before, is that they can build I/O from degree 15 linear maps. I also have new work which I can build I/O from degree 5 linear maps with exactly the SXDH assumption. And both, I think both works would assume locality 5 PRG. Okay. So what is a, yeah?
Locality 4 doesn't exist.
Locality 4 does not exist. The locality 4 PRG does not exist. So locality.
Boolean, but you can also look at algebraic PRG.
Right, algebraic PRG has lower degrees, yes. Okay. That's it. This is, thank you very much. And any questions?
Great, thanks. Oh, that was really cool, very clear. So we have time for questions. Actually, you didn't quite explain where the 6 comes from in this